Hello, general chemistry students, and welcome to the practice worksheet video for the practice exam of the last exam for general chemistry. There isn't any formal final exam, there is just simply exam number 4, and that will be your final assignment for the lecture. Now, essentially, for page 1 of that worksheet, of that practice exam worksheet, is going into atomic orbitals and molecular orbitals. Therefore, part 1 of page 1, fill in the atomic orbitals for each oxygen atom in the diagram below for the last electron assigned in oxygen. What is its set of 4 quantum numbers, n, l, m, and m sub s? Well, this entire blank skeleton is a molecular orbital diagram. Now, the things that are shown in the center, each dash is a orbital. The dashes in the middle are for the molecular orbitals. The ones on the outside are the atomic orbitals. So essentially, wherever you see a line above 2s or the ones above 2p, those are the atomic orbitals. Therefore, that's what we're going to fill in for part 1. And to basically look at those, let's look at the valence electrons. So we're dealing with oxygen, and basically that is in period number 2. Therefore, we've gone past lithium and beryllium. We've picked up 2 electrons from the s block, and then we're going through boron, carbon, nitrogen, and then oxygen. So that would be 4 atoms into the p block. Therefore, we've picked up 2 s electrons, and we've picked up a total number of 4 p electrons. So each oxygen atom is going to have a total of 6 electrons to work with, and we'll just basically start filling those in. So for starting with the 2s orbital, since we're in period number 2, for the 2s orbital, we picked up 2 electrons, one from lithium and then one from beryllium. So cool. And then for the 2p electrons, we picked up 4 of those electrons. Therefore, we're going to fill in each dash, each line once with an up spin electron. And now that we've used 3 of our 4, we can now start filling in a dash or filling in an orbital with a second electron, the second electron being spin downwards. Now, since basically on both sides of the molecular orbital diagram we're working with the same atom, I'm just going to copy all these over and then paste them over here. And that basically completes the filling in of the atomic orbitals. The atomic orbitals are just the orbitals that an atom has just by itself. We haven't gone into molecular orbitals yet. Now, for oxygen, the last electron that we put in to the atomic orbitals was actually the electron in the leftmost 2p orbital, the one that is spin downwards. Now, here's essentially how the here's how the quantum numbers work. N, the principal quantum number, well, that's the energy level for an s electron or for a p electron. That will simply equal the period number that you're in. And well, the last electron that oxygen has is in the p block. Therefore, n would equal the period number, which is 2. Oxygen is in period number 2. Now, the L quantum number, the angular momentum quantum number, L is just going to always equal 1 for if you're working with a p electron. L always equals 1 for p electrons. Now, M, that varies from negative to positive L. Therefore, M is going to vary from -1, 0, +1. So the left, since the final electron was placed into the leftmost orbital, that has a magnetic quantum number of -1. Essentially, it would go, M would be -1 for electrons in the leftmost p orbital, then 0, then +1. The final electron we put in went into the leftmost p orbital, and therefore its magnetic quantum number, or its m quantum number, is -1. And now the spin quantum number, or m sub s, that is simply either going to be +1, or +1/2 or -1/2. Since the final electron that we placed in was spin downwards, its spin quantum number would be -1/2. And yeah, that would be what part 1 is asking. Simply filling in the atomic orbitals, which are the orbitals on the outside of the diagram, and then determining for any particular oxygen the last electron assigned, what are its set of 4 quantum numbers, n being the principal quantum number or the energy level, L being the angular momentum quantum number, m being the magnetic quantum number, magnetic orientation, and then the m sub s being the spin quantum number, the electron spin. Now then, going to part 2 of page 1. Essentially what that asks is correctly fill in the molecular orbitals in the diagram below. What is the bond order for this molecule of 2 oxygen atoms? Well, molecular orbitals are what are formed when atomic orbitals come together, or essentially atoms come together to form molecules, and the way that they do this is by combining their atomic orbitals into molecular orbitals. And essentially, what we're going to see is that we're going to, in this case, see some bonding and anything with a star next to it, and asterisk anti-bonding orbitals. Anti-bonding orbitals simply encourage the molecule to not form. Bonding orbitals encourage the molecule to form, to have bonds. Therefore, essentially what we're going to do is we're going to take the number of electrons that we have contributed from both atoms and start using them to fill each of these molecular orbitals, starting from the bottom and working our way upwards. Well, the 2s atomic orbitals from both oxygens have in total 4 electrons. So let's take a spin upwards electron and a spin downwards electron to fill the first sigma molecular orbital. And then we can continue onwards to take 2 more electrons to fill the sigma star, or the sigma anti-bonding orbital. And that used up all the 2s electrons. Now we can start building our way upwards on filling in the atomic orbitals filling in the molecular orbitals formed from the 2p atomic orbitals. And well, in this case, sigma, we can take 1 spin upwards electron to partially fill in the first sigma. We can take in a spin downwards electron to completely fill it in. Now for the pi orbitals, the pi molecular orbitals, since we have 2 orbitals that are at the same energy level, similar to atomic orbitals, we are going to fill each with 1 electron before we start doubling up. And now that we've essentially filled in both atomic orbitals, we can start putting in some spin downwards electrons. Now, in this case, I'm going to start deleting some electrons because we had a spin down electron already to fill in one of the pi orbitals, and we still have some extra electrons. Therefore, I'm going to get rid of one of these electrons and replace it with a spin down arrow. Basically, that means that a spin flip occurred in order to form that molecular orbital. And then lastly, those pi or molecular orbitals are filled in. Now we still have 2 electrons left over, and we have 2 pi star orbitals, 2 anti-bonding pi orbitals. Therefore, we can simply fill one of them with one of the electrons and fill the other with the remaining electron. That's because these pi star orbitals are at the same heights, at the same level, at the same energy level. That means that each one needs to be filled once before you can start pairing them up, before you can start putting in a second electron. And well, that essentially has just taken our atomic valence electrons and used those to fill in our molecular orbitals. Now, to determine the bond order, BO, that is simply going to be the number of bonding electrons, the number of electrons in bonding orbitals, minus the number of electrons in anti-bonding orbitals, and then divide that difference by 2. So all these molecular orbitals that do not have an asterisk are bonding orbitals. Therefore, we have 1, 2 electrons in the first sigma bonding orbital. We have 1, 2 electrons in the second sigma bonding orbital. And in these pi bonding orbitals, we have 2 of them. Therefore, those are 4 more electrons. So essentially, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 electrons in bonding orbitals. So there's that. And now we're going to subtract the number of electrons in anti-bonding orbitals. And that's essentially any molecular orbital that has an asterisk next to it. Well, we have this sigma star orbital all the way down here at where the 2 s atomic orbitals combined. That has 2 electrons in it. And then the pi star molecular orbitals up top each have 1 electron in them. Therefore, 2 from the sigma star and then 2 from the pi star would be 4 anti-bonding electrons, which basically encourages the molecule to not form. It diminishes the strength of a bond, and we're going to divide that number by 2. Therefore, 8 minus 4 equals 4. 4 divided by 2 is going to equal 2. Therefore, the bond order of this, according to how we filled out the molecular orbital diagram, the bond order for molecular oxygen is 2. It is most likely to have a double bond between those 2 oxygen atoms, which is what we observe through chemical experimentation to be true. Therefore, these molecular orbital diagrams help us justify the orientation of valence electrons in an atom much better than what, say, a Lewis structure does, where essentially a Lewis structure is simply what's a way that makes sense artistically. These molecular orbital diagrams say what makes sense through quantum mechanics. So it's a better way of proving that Lewis structures do actually show what the molecule looks like, but they don't use quantum mechanics. These molecular orbital diagrams do. And essentially, this is all part 2 of page 1 was asking, for you to take the atomic orbital electrons and use them to fill up the blank molecular orbitals, and then using those in the bonding and the anti-bonding orbitals to determine the bond order, which in this case was 2. Now then, going to page number 2 for solution chemistry. Essentially what we're doing is going to be preparing some concentrated solutions, and this kind of math is very important for general chemistry too. Very, very important, because a lot of stuff that we will be doing will involve concentration. Therefore, if you understand this stuff on this page, you are overwhelmingly prepared for general chemistry too, if you need to take the course. Anyways, here's our first solution. A solution was prepared by dissolving 372.4 grams of sulfuric acid in 500 milliliters of water. Calculate the concentration of sulfuric acid in this prepared solution. Well, let's start out with the fact that we know that we have 372.4 grams of H2SO4. And essentially, what we need for concentration is moles of our solute, sulfuric acid, divided by volume in liters of our solvent, which is water. So we need to get sulfuric acid from grams to moles. And that's very easy to do. Essentially, all we need to do, if we have the mass of our sample, just divide it by its molar mass, or multiply it by the inverse reciprocal. In other words, if the molar mass of sulfuric acid is 98 grams per mole, all we need to do is just simply take 372.4 grams of sulfuric acid, times it by 1 mole over 98 grams of sulfuric acid, and that will come out to be 7.600 mole of H2SO4. H2SO4. Which, alright, cool. We now have moles of sulfuric acid. Therefore, to calculate concentration of sulfuric acid, we just need to take the amount in moles and divide it by our volume in liters. In this case, that would look like this. Let's see. That would look like 7.600 mole of H2SO4 divided by our volume in liters, which is going to be not 500 milliliters, but 0.500 liters. Just remember to convert that into liters. And 7.6, oh, whoops, what am I doing? Whoops, my bad. Whoops. So, let's see. Really, it's going to be 372.4 grams divided by 98 grams would be 3.800 moles. Therefore, 3.800 moles of sulfuric acid divided by 0.5 liters, that would equal 7.600 molars, or moles per liter, of H2SO4. So it's really that simple. If you're told a certain amount in mass and you're given a certain volume, just take the mass of your solute divided by its molar mass to get moles, and then divide that moles by the volume in liters to get molarity, or capital M. For this top calculation, going from mass to moles and moles to mass, doing this in the inverse, that is something that you should know after completing General Chemistry 1. It is very important that you know how to do that first top calculation for General Chemistry 1. It's very important that you understand this second calculation for General Chemistry 2. Now then, continuing on to the second solution. Essentially what's being asked is, a second solution was made by dissolving 475.2 grams of iodic acid in 300 milliliters of water. Was the concentration of iodic acid in this solution? All right, cool. Same as before. We know that there are 475.2 grams of iodic acid, HiO3. We're just going to multiply that by its inverse molar mass, 1 mole of HiO3 per 176 grams of HiO3, and that would come out to 2.700 mole of HiO3, iodic acid. So, all right, we now have the moles of iodic acid. Now since we also know the volume of our solvent, water, we can use that to calculate. Our concentration of iodic acid, which is just going to be moles divided by liters. So 2.700 moles of HiO3 per 0.300 liters instead of 300 milliliters. That would come out to 9.000 molar of HiO3. So 9 molars or 9 moles per liter iodic acid. And that's the two calculations right there. Again, that first calculation of grams to moles is very important for General Chemistry 1 for you to understand that by the end of this course, because it'll be very influential in Gen Chem 2 and especially in organic chemistry. If you do take that course, it'll be very important to understand this calculation for the lab component of organic chemistry. And then this second equation of determining concentration from moles and liters, that's very important for General Chemistry 2 and exceptionally important for organic chemistry lab if you do go on to organic chemistry. Now then, we basically determined the concentration of dissolving a certain mass of something in a certain volume of water. Well, let's do a dilution problem, which is essentially we take those two solutions from part 1 and 2 and we mix them together so that their volumes combine. And we're assuming that they're additive, which means that if you take half a liter of one and 0.3 liters of the other, they add up perfectly to 0.8 liters. Not always the case, but we're going to assume it happens in this case. Therefore, if we're essentially raising the volume by combining those two solutions together, how is the concentration affected? Well, once again, concentration is simply moles of one thing divided by its volume of solvents. So, if in the first part we determined that we had 3.8 moles of H2SO4 of sulfuric acid, and we originally had it in 0.5 liters. Well, we essentially took that half a liter solution of sulfuric acid and mixed it with that 0.3 liters of iodic acid, which means we have 500 milliliters added to 300 milliliters, or 0.5 liters plus 0.3 liters, which is essentially saying we're taking 3.8 moles of sulfuric acid and dividing it by the new volume of 0.8 liters, which that would equal a new concentration of 4.75 molars for H2SO4. Now, as for the iodic acid, that's going to be similar as well, because in part 2, we determined that we had 2.700 moles of HiO3 of iodic acid. We're going to divide it not by its original volume of 0.3 liters, but by the combined volume of 0.8 liters, which is essentially 0.5 liters from the sulfuric acid solution plus 0.3 liters of water from the iodic acid solution. And that will come out to equal 3.375 molars of HiO3. So that is simply how to do a dilution problem. That is an example. Just simply know the moles that you're working with. That does not change when we combine our two solutions. We still have a certain number of sulfuric acid. We have a certain number of iodic acid. it's not like we're combining an acid and a base together, which partially cancels out one with the other. We'll do stuff like that in general chemistry too. But for this case, we're just taking an acid with another acid, we're combining them, and assuming we still have the same number of moles of each, there's just more water diluting their concentration. Therefore, we went from 7.6 molar sulfuric acid to 4.75 molar sulfuric acid concentration, and we went from 9 molar iodic acid to 3.375 molar iodic acid. Therefore, that is simply how to do these guys right here. Now, that is essentially the practice worksheet. Just a heads up, if you would like to continue learning through my particular teaching style, or if we do happen, or I should say, if you are having one of my courses next semester and we go online during the semester, these are the kind of videos you can expect. It won't be me showing myself personally, but basically me narrating what is on a PowerPoint and basically screen capturing and screen recording what is being shown. That way I only show you the information that I want to talk about and you still hear me discuss it versus just having you read stuff. And just a heads up, so far I have been told that I will be instructing the on-campus General Chemistry 2, that's Chem 152, specifically Section 101. I am not doing the online version, I'm doing the in-person version, and that would be Section 101 for both the lab and lecture. If you also need a physics course, I'm doing General Physics 1, which is Physics 131, both the lab and lecture, and I'm also doing Physics 1 Calculus-based, which is Physics 151, lab and lecture for the spring. And there will be various other chemistry labs that I'll be instructing. I have not been informed specifically what those will be. So essentially, if you like the in-person teaching style or you prefer this manner of doing things where it's simply, if we go online, it will be simply a video of the PowerPoint with my narration versus, say, a video of the instructor showing themselves talking about something. Hey, this is what you can expect if we go offline if you have me as the instructor. Otherwise, you'll have me in person, and I really do look forward to having as many of you once again for General Chemistry 2, regardless if I had you for lecture and lab or just the lab. So, with that, without further ado, getting close to getting just past the 28-minute mark, it is a pleasure to have had every single one of you for this fall semester, this global pandemic. You guys are all very pleasant to be around, and I hope to see genuinely as many of you next semester as possible, regardless if we're in person the entire semester or we go online. Whatever the case. I enjoy all you guys. Goodbye. Or, nah. See you later.